Our next speaker is Richard Elling. So Richard comes from the Sun Microsystem days. So he's been exposed to ZFS from a long time ago, and he's been playing around ZFS and doing some changes for many years back. So today he's going to talk about observing and monitoring in ZFS and how to improve in that aspect.
Thanks, and good to see everybody here again this year. How many years has it been? 6? Wow. Very good. Glad to see a lot of familiar faces. Like many of you, when we deal with people with issues and so forth, and or monitoring systems, especially with systems demonstrating malbehaviors, it's not uncommon for us to come back and someone comes on the net and they say, hey, look, I have this problem, and then you go back to them in the canonical send me the logs question. And so what I'd really like to do from this, or what I'd like to see I get out of this presentation, is that we move a little bit further upstream towards more modern monitoring and observation tools in the community. And so I won't be getting a zip file with 6 megabytes of logs that I have to dive through and understand. So that got me started on this, and then some other tools. The good news is all this stuff I'm going to discuss is open source, except the spell checker apparently. But to me, telemetry is very important, and it's been a while since I worked on the space shuttle program, but STS stands for Space Transportation System, which is more commonly known as Space Shuttle. And we have a lot of telemetry in there, and this is a failure mode, or the result of a failure. STS-107 is Columbia that burned up on reentry when the wing burned through. And this is the telemetry where you can clearly see that that was not normal, right? We have a bunch of normal flights, and then we have the flight that was abnormal. And this happens to our ZFS systems in the world as well. And so the question is, how can we not only capture this, deal with it immediately for operations, but also forensically, how do we go back and understand what happened back in time? So it's very important, and at NASA we collected a bunch of telemetry, all kinds of telemetry, and stored that stuff forever. And so they were able to go back through and get that information. So how can we get that back into our daily life in the ZFS community? And I'm going to focus primarily on ZFS on Linux, because that's where I've been working most recently. Those in the Solaris or Illumos environments know that kstats have been around for a long time. A typical system in Illumos will have 45,000 kstats, something like that, available for you to peruse and enjoy. When the port was done to Linux, Linux didn't have kstats, and so nor did Linux have, at the time, really the sys event infrastructure that all came as part of Illumos fault management architecture. And so fortunately, that was fairly easily portable into something that sort of resembled what we can do in Linux. So in Linux, then, we use a pseudo file system under proc to represent the kstats that we would normally have seen in the kstat system in a Solaris system, which is really cool, because now developers can add new code, add new stats, and then operations people can grab those and then understand and monitor them. It's an example. Love the font conversion. This is an example then of what you actually see in a Linux kstat file. You'll see some metadata in the first line, then you'll see not quite. This is a proportional font, no doubt, but you'll see a name type data as a tuple, and then until recently, all the types were 4, which is unsigned int. Recently, we started adding in some strings, so you'll see type 7. So if anybody's written code that assumed that 4 was always going to be 4, surprise, it's not. It is, in fact, the data type. And so most of then what we see is unsigned int 64s for kstats and ZFS on Linux. That becomes important soon. And there's also a few command line tools that you can run to observe these things. So in the ZFS on Linux tree, there's zpool iostat, of course, built into the zpool command. There's a couple commands out there with history that goes way back that have been carried along. Arcstat, arc summary, tell you a lot of information about the arc and how it's currently using all your RAM. Debuff stuff, or stat and SPL slab are a little bit more developer friendly, or maybe developers are more interested in that than say operations people, but they're there. And then of course in the performance world, there's you'll always hear us say, so can you give us the iostat minus x output from that? And the reason is it shows us the device stats, including operations, reads, writes, operation counts, but most importantly, latency, or at least an average latency, which is the first place where we go to say, hey, your average latency is 1.3 seconds. You might have something wrong with your disk. And so we see that a lot. In the ZFS on Linux world, it picks up zvols as well. So people who are looking for instrumentation for zvols, bandwidth, and latency, it's all right there in iostat minus x. And then there's a couple other that are a little bit more specific. zfetchstat, which just looks at how well your prefetcher is working or not working. And then there's one you may not have heard of, few people have, that I wrote called Kstat Analyzer, which started in the Illumos space, and it tries to do a performance guy analysis of, I see all these stats, I correlate them, I pick out some information, and not only is your disk slow, but it's actually only one of your 8 disks is slow, kind of thing. And Kstat Analyzer, I've ported over to Linux, and we'll be making that a little bit more full-featured over my gratuitous spare time. So that's what you can get command line. There's probably 1,000 others out there as well. It's pretty easy to write a tool to scrape that stuff. But we really want to use our eyeballs, right? And so what I'm going to talk then about is really 3 stacks or 3 major components of modern databases and monitoring tools. One thing, I've seen a couple of slides, I think Christian showed that using Prometheus with Grafana. Grafana is by and large a terrific open source project to help us guys take telemetry and other data and present it in dashboards. Really good stuff. Can't recommend it highly enough. Then the other 2 are Influx Data's tick stack, which is Telegraph, InfluxDB, Chronograph, and Capacitor. And the other project you'll hear a lot about is Prometheus, which comes, where's that originally from? Yeah. So it comes out of the cloudy space, and they're a little bit different, but I'll go over those and why I end up using both in my architectures. But an example architecture of how we're going to put this in is we'll have nodes out there in the world. They're going to have some sort of aggregator or agents that collect this information. And then we're going to push that up to a database somewhere and then look at it with Grafana, right? And then it turns out that, well, there's various and other major components to this architecture. And those are really the push versus the pull. And Prometheus is a pull model. So the Prometheus queries an endpoint and it gets the stats back. And then a while later, he goes and queries it again, gets the stats back. Grafana can do the same thing. So I can go to a Prometheus endpoint directly from Grafana and query, that sort of thing. The InfluxDB and Telegraph are push. So it's going to collect data all the time, and then it's going to periodically send that up to a database. And so it turns out that there's not a perfect case for either one versus the other. I just end up using both, and these are the two I use. So let's start with seeing the data. Grafana renders in the browser, which means that once the data is transferred across the network, then you can do some operations and you can peruse the data and look at it in more detail, all in the lovely confines of your browser. It uses JavaScript, and so it pretty much runs everywhere. In the sense that JavaScript in the browser runs everywhere. It actually turns out to be quite good even on small phones. So that's pretty cool. It's got a plug-in architecture, lots of community stuff. Check it out. It's good stuff. I store stuff then into a time series database. And in the old days, we would have used SQL or MySQL. You'll see some old people talking about using things like Cassandra, databases which really weren't specifically designed for time series, but nowadays we recognize the need to really focus in on doing a real time series databases, and they're becoming commercially viable and big open source environments. So the difference between the two, InfluxDB versus Prometheus push-pull that I discussed a little bit earlier. They've got query languages. To me, the most important thing is data types. So you remember earlier today, George was talking about the ZIO pipeline. And where are you in the ZIO pipeline when you get an error? Well, you'll get an event with that error, and in that event, it will tell you where in the pipeline, which pipeline stages you were instructed to go through and where you are in that pipeline stage, which is really useful information. It's an integer, right? It's an enum stored as a bit field. And the problem is now if I store that as a Boolean, or certainly I won't do it as a Boolean, but if I store it as a float in Prometheus, then I have a different version now that has a different pipeline set. Like suppose we add encryption. Now that number doesn't make sense unless I also know which version of the OS that came from. So why do I like data types of strings? As data types of strings is when I generate that event information, I can decode it and then give you a string that says, these are the pipeline stages, da da da, and this is where you broke, da 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 da, and it comes out and nicely gets stored in my database. So the other thing you'll notice about Prometheus and its float issue is we do high-speed data systems at New ISIS, and so we look at counters. So just, for example, bandwidth counters, right? I'm counting bytes going across my I/O data path. For the high-speed systems we have, I will roll over 43 bits of a mantissa in just a few days. Right, and on the systems we have on the drawing board, we'll roll over that counter in maybe 2 days. And it's just not going to fit a float. And so that's a painful thing. But in InfluxDB, we do have ints, int64s, so we can use those natively, which is cool. Collectors, agents, and aggregators. There's two that I mention out here. These are the two that I keep track of in trying to keep up the ZFS on Linux data collection with those. And those are Prometheus projects has a node exporter, which puts out the generic set of I/O statistics, network bandwidth, CPU memory, those kind of things for a compute node. And then there's a ZFS plugin for that, and it will give you all the ZFS data. And then in Telegraph for the influx data environment, it also collects most of those things as well. I'm able to convert those strings to enums as strings, so they're a little bit more useful. But both of those are there, and as of my Christmas project was to get those up to date on as far as where we were on Christmas of 2017. So that should be pretty up to date, and those are out in the released and supported versions, which is pretty cool. So then let's take a look then at what an example might look like for an ARC problem that we were discussing just last week. And so I've got a couple of dashboards that show then my ARC activity, and then on the bottom, which I really want to draw your attention to, the bottom of that is a single, if you have enum data, then you can graph it as a stripe, and then it will change various colors depending on the context of the value of the enum. And so in the ARC we have this thing called no-grow, and it's a Boolean, so I only have two colors, sorry. But basically there's times when the ARC has been asked to shrink, and then for a while it's going to not try to grow again. And then that's when no-grow is ticked over to off. And so it goes into a phase where it won't grow. And so you can actually then see that in the bottom where we were growing the ARC, then we got to a point, we started to reduce the ARC size. This is what we still need to figure out. Then we tip over to a no-grow phase. And then after a while, there's a timeout for no-grow, and then it's allowed to grow again. You can see it grow a little bit, and then it comes back down and it goes back up. So this is the kind of thing that when you look at it this way, it's immediately obvious that, oh, I have a problem here. And we are working on this problem. It's annoying, but it's not, it's a new thing, so we know it's something we've introduced. And so by contrast, if I had been into an email conversation with somebody and I said, well, give me the arcstats, and then it's like, no, not those ones. I need this one. I need to know what arc no-grow is, and I need to know, these various levels for these other parameters. Then, in fact, I wouldn't be able to, it would take a week to get through that email chain, right? But if they had all the data always collected and it's all right there, then I can just say, pull up this dashboard, or I will email you a dashboard. You take a look at the time in question, and then we can dive into it further. And with that, I'll make a shameless plug for tomorrow. The people at the hackathon, we start to peel this onion when we start to look at this data. And when I have all the stats available at my fingertips in a database back in time, going back 2.5 years, for example, in my lab, then we can ask questions now that we could ask of the experiments we did 2 years ago that, in fact, we didn't understand might have been a problem back then. And we can go back and take a look at that thanks to the databases. And there are new dashboards, and we can deliver new analysis as well. This is another ARC example, same sort of thing. And we can show clearly hit rates and that kind of thing. And since this was done in the browser, when I hover over a particular time point, you can actually see all the values out numerically. And so, this is very useful. It becomes very interactive in these things when you start to get into it. And so tomorrow, those who are interested at the hackathon, we can go and do some stupid pet tricks. Here's another example then of IOstats. This is the graphical version of that which you would see scroll off a few pages of text if you ran iostat -x. And this is just a transition from I was doing random writes, and then we started to scrub. And these are hard drives, so you can kind of see I went that. And I really wanted to point out that we start to view these things differently. And on the bottom graph, I use a model where writes go down. So I use a negative y-axis for the writes, and then reads go up. And so when you do that, it's very obvious then when I look at the graph, am I writing versus reading? My brain will tell me. And then if you look at the total bandwidth when I'm doing both reads and writes, I can get an appreciation of the total bandwidth in the system, all without looking at any numbers, right? Let your eyes do the math for you. And so that's an example then of we did some random fills and we did some scrubs. So next I want to talk about when I build the dashboards, the ones I release out to people. At the bottom row of the dashboard, I put some documentation in. And we can do, it's markup for those who are interested, so you can get a little bit fancy with the documentation. Earlier today we were talking about the ZIO pipeline and briefly mentioned the fact that we break these IOs out into queues, and then we, so we have 5 queues for sync read, sync write, async read, async write, and the scrub queue. And then those all merge back together and get actually sent down to the disk, which also has a queue. And then we kind of want to be interested in understanding where are we spending all the time, because we have these tunables in the scheduler, but to date, I don't think anyone actually has really changed those very often. We do in performance tuning sometimes, but we really didn't have a very good understanding of why and when we should in fact adjust these, because since you're trying to adjust, you know, how we're going to fill this queue to disk, you kind of need to understand what's in the queue during my experiments, and then also what do I want it to look like at the end, right? So what is it now and versus what I want to look at. And so if you look in Z pull iostat -w on Linux, you will actually see a histogram then of the latencies in all of these queues. Again, great font translation. But trust me when I say that you will see these things, and we gather this data for not only every, or the top level, which is what I'm showing here. When you do a zpool iostat -w, you get the top level roll-ups for all of the VDEVs underneath. But in fact, in the system, there is in fact every VDEV all the way down to the leaf VDEVs, a histogram for all of these queues. So then how do we look at these in a more meaningful sense to the human eye? And we do that with some people call these heat maps. Some people call heat maps other things. Heat maps well overused in the groups that do dashboards. You'll find heat maps that don't do anything like you thought new heat maps. But these are latency heat maps, made very famous by early work in Joyent a few years ago, and now readily available to you. So this is the same data over time in the queues. So at the end to end, we have the top level read and write latencies for the pool. And I did it in this dashboard. I did reads on the right, reads on the left, writes on the right. And then I color coded them just different colors so that once you got used to using the dashboard, you could immediately look up and say, oh, I'm having a problem with writes, before you even got into the details of the data. So in this experiment, which I just ran on my laptop on the plane over, I was doing a fill of a small pool, and then when it finally filled up, then I did a scrub. And so I kind of brought out for this time period, at the top level, then we see a bunch of writes, and then at the top level, the scrub does a bunch of reads. Okay, so that should be pretty readily, hopefully intuitively obvious. When we go down, then the next level down into async, sync, reads versus writes, for the next level down, then you can really start to see it break out. So you can see clearly that we've got synchronous reads going along. The only async read that I'm aware of is a prefetch, right? So the only time you're going to see all reads are basically synchronous, is the lesson. And then we have scrub reads, and scrubs have a intentionally lower priority than the others. So these are the queues waiting to get to the disk, okay, for the 3 columns on the left side. And then the actual disk queues are on the right. And so what you can clearly see, or I tried to intentionally show you, is on the scrub read queue, you see there's a few IOs or few residency times in there that are down around the 2 microsecond kind of range, and then the bulk of them are way up and around, 8 microsecond or 8 milliseconds or so. And no, sorry, you can't read the legend. But it's time going up from microseconds to milliseconds to seconds on the y-axis. And we get a distribution across there, and you can see that a whole bunch of these IOs are queued in the scrub read queue for 8 milliseconds kind of time frame. And if we were looking at that versus the other queues, then it becomes interesting. Do we need to bump up the priorities for the scrub queue or not? I don't know the answer, but this is where I can kind of get a feeling for that. And then similarly, on the bottom row, we have writes, and you can see the writes coming through. And I filled up the pool, paused for a little while, and then did a scrub. So you can kind of get that. So hopefully, if we can get more and more people to take a look at these, especially when you're off tinkering in the lab with new code, and a repeatable workload, and even some ZTS stuff, then we can get an idea, is this really an improvement? Is it doing what I think it is? Is it moving to the right queue? And so forth. So with that, I'll ask for some questions.
Is it 3 questions as well?
And then I've got some references that are there as well. So any questions? I have a question. So how am I going to get this to you guys? I'm going to put together a page that kind of tells you how to build and get to the point where you can collect the data. And then I've got somewhere on my GitHub site a start to a series of dashboards that are specifically oriented toward my ZFS work. And then there's a few dashboards in the public domain out there on the Grafana dashboard list that do some ZFS work that's pertaining particularly to the tried and true collectors that have been around for a long time. Collecting things like arcstat and so forth has been around for quite some time. But then the new stuff for the latency histograms, I need to push that. So Mark.
You said you've been collecting over like 3 years of data here. What kind of volumes of data are we looking at for your keeping?
So how much space do I need to store all this stuff? It's surprisingly compact. So one of the things, most of my data is stored as InfluxDB, and InfluxDB has an extraordinarily compact ability to compress the data, since it knows its time series and it knows the types, and it really compacts that quite well. I've got 2.5 years of data on, I'm up to about 140 machines right now, and it's using about 200 gigabytes of disk space. There are people who are building these things at million nodes kind of level, so maybe a few terabytes. It doesn't sell much disk, unfortunately. Yeah, question?
Yeah, so Richard, how do you parse the data to feed it to InfluxDB? Do you have some sort of specialized parsers you use, or does InfluxDB provide some sort of pre-parsing tools?
So the question is, how do we parse the data and get it up into InfluxDB? And the way it actually works is, inside Telegraph and inside Prometheus Node Explorer, there's a ZFS agent that will read the kstat files and then convert that into the format for the telemetry stream that's given to you. So, it's a transformation kind of workload. It's not high rocket science kind of thing. The biggest impediment to us doing more and new of these is, how do we get the code actually, how do we get the developers to add instrumentation? Yes, because as George mentioned earlier, we would, in the Solaris Illumos space, we would do dtrace, right? I need something, I got dtrace, I'll whack out a quick one-liner, I'll take a look at some stuff, and I'll forget about it. But some of those things are quite important, and they're very useful to have. And then we start to put our operations hat on, then we start to think, what would an operations guy want to know such that they could know there's a problem that needs to be attended to? And for that, we're still lacking quite a bit of coverage in the environment. And anybody who's willing to work on that, it's not a free thing. Like dtrace is not free, eBPF is not free. But if we do judicious use of instrumentation in the code, then we can get a long way. So, Prakash.
Do you have any thoughts on how to bridge the operations gap and the developer gap if you have a lot of data and you think something's going wrong? How do you help explain why such that we can fix the problem? Because sometimes I see a big gap. We can see something's wrong, but we don't know why, or even something's right and we don't know why is it right.
How do you bridge the dev and ops gap? Oh. Is the bar open? No. The approach I've been taking lately, with a little bit of success, is to get the right level of dashboarding, and more importantly, another portion of monitoring I didn't touch on is alerts, right? In my example of when we had the Columbia accident, that was obviously a red alert kind of a situation, and you want to get those early as can be into the operations sense. And at the same time, there's an operations group that usually does capacity planning, and you want to help the capacity planners predict how much more gear that they need to buy from New ISIS. And so all these things are very useful for us, and we want to do that and to help that. And so we have different consumers for the data. I mostly do performance work, and so in the performance work I care entirely about latency. All right, not entirely, mostly about latency, because that's where it's most painful. But for an operations guy, maybe they care about, what is my daily increase in load, right? Which is a very different question. The tooling can handle both, and then it's a matter of, all right, how do I communicate a dashboard that makes sense, right? If we talk through dashboards, is kind of the way I've been trying to approach that going forward. Now, for forensics or figuring out why it broke last week, I'm of the opinion, don't delete anything. So I'm like, oh, I collected all this data, right? Every 10 seconds or 15 seconds or 1 second, depending on what it is. I don't ever want to delete it, which is why my lab has got this database that's been around since I started working there. But that becomes impractical at large scale. And so those guys want to downsample and all that. So there's ways to do that. Fortunately, most of the things we do in ZFS is counters. And they're unsigned int, 64s, they're always going to go up. And so they're easy to downsample. I can just take a sample and throw away an intermediate sample and still retain that growth over time, which is really cool. To developers, gauges are troublesome. Averages are appalling. Incrementing counters are good. Just take a count. We love it. Any other questions?
I think
We're out of time?
Yeah, we are out of time.
We're out of time. Thank you, guys.